Good morning. The aim of this talk is to understand how this kid from Romania came up with whatever the hell he came up with, and so I want to. That's what I'm going to go after. But first, let me make this work. How do I advance with this? No. How do I advance? This one. All right, there we go. That's good. Okay, so this is I break it up in four parts. So I'm going to celebrate Bejan a bit, what he did, and then I'm going to look into what he did, what the basis of it was, and then I have some problems, which I was just discussing with him, about how he's interpreted or represented what he found, and then a little call to action. So, yeah, I say when Bejan came up with this constructal insight, it was like a dam breaking, and all of a sudden he had all these ideas came out of it. Now, what I want to celebrate right off the bat is I've been working on some of these problems, like the arrow of time. The number of articles on this is just huge, thousands, and they all miss it, but Bejan gets it right. Some of them guess it, but Bejan gets it right. This is enormous. This is huge. Totally, very light recognition. That all change is an evolution of a design, so forth. Also huge. And design, by its very nature, is continually morphing into a better design. This is huge. I'll come back to it. Another one that I worked on a lot, principle of least action. The amount of nonsense written on this is just incredible. Bejan gets it right. He sorts it out, and he goes after Lagrange and so forth. And this is huge. So he should be enormously celebrated for these things. People don't mention this much. Oops, whatever happened to that? Did I do something bad? There it is. How come I'm not getting the next slide? Because I'm dumb. Doop doop. Did I hit the wrong button? There it is. Sorry, I was hitting the wrong button. So these are other things, and given that I timed this thing out a little while ago, it was an hour, so I'm going to just go through these things real quick, and I just not even mention optimization and design and so forth. So real quick on my background. So I started in astronomy, and then I felt it was too narrow, and long story short, I morphed into philosophy of science. And I didn't really like philosophy of science. I didn't really like the scientific worldview in general, because I didn't see myself in the scientific worldview. I mean, all these laws and deterministics. So I said, there's something wrong with that. And so gradually I morphed into philosophy of engineering. These guys down below are sort of my mentors, the guys I work with and stuff. As I was trying to find the limits of science, what's wrong with science, I was like, well, there's something about reversibility and irreversibility. So I kind of started looking at thermodynamics. And this is one of my mentors, Peter Atkins up at Oxford, has tons of books out on thermodynamics. And he says in this book, he says, Carnot and Boltzmann epitomized thermodynamics. Carnot traveled towards thermodynamics from the engine, then the symbol of industrial society. Boltzmann traveled to thermodynamics from the atom, the symbol of emerging scientific fundamentalism. And then he says, thermodynamics still has both aspects. Now, I was a little surprised at that. I was taught that, Carnot was like this, caloric, was some sort of afterthought, that the real thing was the Boltzmann, Carnot, or Clausius-Boltzmann stuff. So, and then he points out that these two versions are not compatible. So maybe one is a special case of the other. I don't think that turns out to be right. So my theme that I've been working is engineering thermodynamics, which is from Carnot, is actually a more general concept of thermodynamics, and it both subsumes and supersedes all the mechanical formulations. Subsume means it can account for everything that the mechanical versions of thermodynamics can. Supersede means it understands the old thermodynamics in a new way. This is a tricky part. I think, and so this is another guy, Cardwell, who was at the seat of the Industrial Revolution in Manchester, And he basically says the same thing. I'm going to skip that over. So what was Bejan's insight? This is the thing. So he talks about it a lot, and I've just been reading all his books in particular. And one thing I really like about Bejan is he's very honest about this. He's like, I really, even later, and I think in Time and Beauty, he goes like, I really didn't know what I had. And so his understanding of what he had, what happened there in 1996, has developed, has flowed, if you like. But the one thing he finally comes down and he says, what's really important here was the concept of the finite. And he goes through various examples of rejecting infinitesimals as not real. But he also knows that infinitesimals are linked to reductionism and mainstream science, what we call mathematical physics. And all of the mathematical physics is differential equations, which is another way of saying they're all based on infinitesimals. So what I want to do here is follow his embrace of the finite. And so the way I want to get at this is that there are two traditions, the analytic and the synthetic. And in my way of going after this is in terms of completed infinities and incomplete infinities. So in a completed infinity, if I have I have the circle, and I'm going to put all these polygons in the circle, and to get the area of the circle, and it's going to more and more sides to the polygon, and as those sides increase to infinity, at infinity, then the polygons, then there's the circle, and this is sort of integration, if you like, so there's a problem there. For me, I used to call it jumping the asymptote, which is to say that when you do that linear stuff, it doesn't ever really get to the circle, but if you just say, oh, yeah, I got to the circle at the limit, well, you've jumped an asymptote there. Now, the synthetics guys say, no, you can get as close as you want, as close as you want, as small as you want, so forth, but you don't ever get there. And so that's the synthetic tradition. And so where does it go? So in the analytic expression, circles, the properties of circles can be expressed in terms of lines. So in a sense, we're reducing circles or the curvilinear aspect of reality to a linear aspect. This is big in what Lagrange does. And it's calling jumping the asymptote. And the problem is when you do that, you're erasing the difference between lines and curves. Okay, and this is a big part of what Archimedes goes, because lines and curves are, if you like, incommensurable. They're different, they're opposite, but you're not going to, if you try and reduce one to the other, you're going to get in trouble. So for Bejan, it's crucial to be in the synthetic tradition because you need those two things. You have the finite, you need those two things in order to have optimization. If you don't have that, so you don't have any optimization, it is not a word that gets used in mathematical physics, at least in the relevant sense. Now, just commenting, these opposites that get lost in mathematical physics, modern mathematical physics, reemerge, however, in quantum theory. And Adrian has not launched into quantum theory yet, although he's I think the Constructal thing will allow us to make more sense of quantum theory and relativity, for that matter. So this is a piece I did for the thermodynamics thing. You can see it on my ResearchGate thing. So anyway, it's the same basic thing. If you want to understand quantum theory, you have to get to this participatory systems engineering thermodynamics framework. Okay, so Archimedes, I covered this. One of the things Archimedes does, when he does this, when he goes after the area of the circle, he both inscribes and circumscribes. And he goes both those, and he kind of pulls those together, and they're like, they're these asymptotes. And so that's where he's looking for the propositions, which for him, I want to suggest are optimals. And he talks about the intersection of the asymptotes, which should ring a bell here somewhat. Again, as close as you like, as small as you want to get. And one of this guy Heath says in Greek, ancient Greek mathematics, they had a horror of the infinitesimals. Why? Because for them, the reality was made up of these optimals, of these things that were in between. Okay, so and there's a famous essay that came out, Archimedes' method, which he discovered, and in that he discusses the relationship between analytic and synthetic. He says, well, yeah, okay, I use the analytic occasionally, and it's a method, like the way people do today. But he says, I'd never trust it until I had translated it into a geometric proof. And what's he doing there? It's sort of like, this is one of the things, and this curious insight that Bejan mentions is that there are a lot of people that understand or seem to understand these things like the mechanism of scaling, hierarchy, power laws, all this sort of stuff. But they don't understand them in some sense. And this is kind of what I think Archimedes is saying too. Well, you can get these analytic representations of these things, but you don't really understand them until you get the constructal version. So I would say. Very quickly, also, let's see here. So just that all the scientific laws since Newton are differential equations. And one way to say this, Atkins got me on this, the linear motion in Newtonian physics, the three laws, is by infinitesimal linear steps. Okay, so it's a differential statement, and so if it's differential, well, when you take a differential, you leave something out. Well, what gets left out in this linear physics? And I would say what gets left out is the curvilinear aspect and also the time aspect, which comes up more. And if you try and sum all these infinite steps, each infinite step is just an instant, and you sum all the instants, you don't get anything. It's really nothing. This is Zeno's paradox of the arrows and so forth. So the science is not the way the real world works, and so okay. So and just for a heads up to people, the best treatment of this discussion of finite and infinitesimal is in Lazare Carnot's essay, Reflections on the Metaphysical Principles of Infinitesimal Analysis. And there he goes in, he's very clear about as small as you like and so forth. And he also brilliantly, so to speak, justifies the use of the calculus, the completed infinity calculus. He says, that's very useful. Just don't take it as, representative of the whole system. And he kind of goes after Lagrange, he sort of pats him on the head and moves on. So real motion, and this is the key thing, I think, the idea of motion for Adrian is that it always has two irreducible, opposite, continually balancing components. And in modern, later terms, the relationship of translational and rotational components. And I think by analogy, this is particles and waves. So when they happen in this earlier period is Leibniz came up with this thing called the meta shift. He shifted from statics to dynamics. And it's meta because we have paradigm shifts, Kuhn's paradigm shifts are always supposedly within science. A meta paradigm shift because he's going from science to engineering. From statics to science, engineering, dynamics, as I'm going to pitch it. Princeton historian Gillespie characterizes this period as sort of, I say, ultimately 1650 to 1850, as this transition from the statics, the science of mechanics, to dynamics, the science of machines or engines, as it comes out. And the mature Leibniz talks all about engines. And it's engines, the ontology of the world is engines all the way down. And if you like, engineers all the way down. There's something I've called Carnot's epiphany, which is we're engineers in a world of engineering. If you like, we're agents in a world of agency. And there's an analogy with Dewey's switch from this static as this spectator view of what we're doing as inquirers versus being inside the system. We're asking different kinds of questions. What am I going to say here real quick? How's my time? Not too bad. Okay, so anyway, you get. I'm going to try and pick out things that Bejan came across too. One that he's moved to a holistic system. You have A hits B, and we want to know what happened to B in Newtonian mechanics. But in dynamics, A hits B and B hits A, and he talks about Don Quixote and so forth. So, And fairly late, I'm not sure it is, Bejan, instead of talking about the system and the environment and the interplay with those, which is typical of classical thermodynamics, Bejan goes like, oh, wait a minute, these are actually one thing. And I think that's a major advance in understanding the thing. Okay, I'm just going to go on here if the thing works. There it goes. So I would say also I was talking to Adrian about this earlier, that this guy, Lazare Carnot, who was the organizer of victory, he was a military general under Napoleon, but he also had a prior life or a separate life as this incredibly genius mathematical engineer. And and he does a couple of things. He has this great essay, and he says, there's a well-known principle of engineering practice that there's a trade-off of time, of velocity, and strength or power. I mean, if I use a pulley, I can get it up faster or slower. And then he goes on and he says, this, everybody knows this. There's a trade-off like this. And he says, but there's none of the rational mechanics has any explanation of this at all, which I think is true. And he also points out there are no engineers in the rational mechanics, anyway, I better go on here. So he's trying to give an engineering worldview, and there's a little redundancy and all this sort of stuff. So the engineer, because what he sees, he puts this time in there, this time, velocity, strength thing in there. It means that as an engineer, I have options. I always have options. I can achieve a task one way, achieve it another. So the engineer has options. This is a constrained freedom. Doesn't mean he can jump to the moon, but he always has the ability to approach a task one way or another. This is, I think, the free will. And so the path to the future is, in some sense, indeterminate, a nice connection to quantum theory. Okay, so go. But this is engineering. Engineers have choice. In other words, choice and all these things that Bejan is always saying. So here's my problem area. So this is, is Constructal law science, physics, or engineering? And it's not science. Like he just trashes science. I mean, classical science. He just says, he explains to us why it's nonsense. And nonsense, extremely limited, not representative of the whole, if we can say. So, and what I've struggled with, Adrian, I feel your pain trying to sort this one out. This relationship between science and engineering. How is engineering just applied science? Is science engineering research? I mean, what is it? And you go in, and the same question here is the relationship between analytic and synthetic. And it also is a relationship between two representations of knowledge. And also it's the relationship between classical, this Boltzmann, Gibbs thermodynamics and the Carnot thermodynamics, the mechanical version of thermodynamics and the real thermodynamics, the engineering thermodynamics. So, and my new mantra here is you can't get there from here, you can't get here from there. So, which is to say, there's no way to get to the Constructal or to get to engineering thermodynamics from the classical reasoning, from within the mechanical framework. So this is, Bejan is correct. He says the Constructal law is the first principle. So you can't get it. You can't get it from the established science. So you're going to have to add a principle or something like that. Well, I'm all for that. But the principle is, in some sense, conceptually more sophisticated and more comprehensive. It has things like freedom and evolution. So those are concepts that are just not there in the classical presuppositions of classical science. So I want to argue that the Constructal law is, in fact, an engineering, a real key to understanding engineering thermodynamics, and engineering is the bigger tent, not physics. So engineering is the bigger tent, science is within it. Okay. Now, Bejan is one of the reasons he's bothered, he doesn't want to leave science behind, okay? Nothing left behind, he says. And this is, Bohr says, invented this thing called the correspondence principle. The correspondence principle simply says that any later theory you have needs to be able to understand the successes of the prior theory, okay? So that just means subsume. Now, the problem we have, though, is science has been misrepresented totally. So there's subsume and supersede. Subsume means, yeah, we're going to be able to bring it along. Supersede means, but we're actually going to understand it in a conceptually new, more sophisticated way. which I think is really. Now my suggestion to Bejan here on Nothing Left Behind in the engineering version is this idea of recursively enabling. Engineering evolution is recursively enabling. So each advance is the next one. Am I way over time? So a colleague of Bejan's at Duke, who I asked Henry if he knew Bejan, he said no. I asked Bejan if he knew Henry, he said no. They're in the same department, Duke. So, but anyway, Henry's written like 25 books in engineering. He's one of the philosophy of engineering people. So, and he deals with these. He says everything you thought of as science is actually engineering. And the reason for this is there are no inquirers in the scientific worldview. I mean, it's not. We say it's not self-referentially coherent. It can't. The scientific world cannot account for itself. Okay, it's totally deterministic. It has no inquiry in it. It has no knowledge. Doesn't make sense in it. So it's not so. But the engineering view with engineers in it is self-referentially coherent. And I say all knowledge of the world. So here's the other thing. This guy's seminal. I hope you all read this guy. Walter Vincenti, What Engineers Know and How They Know It. I have to read this to you. Modern engineers are seen as taking over their knowledge from scientists and by some occasionally dramatic but probably intellectually uninteresting process using this knowledge to fashion material artifacts. And they said, from this point of view, studying the epistemology of science should automatically subsume the knowledge content of engineering. Engineers know from experience this is not true. And it goes on, he says, engineering knowledge is not derivative of science, but an autonomous body of knowledge. Late Bejan, he says, the knowledge based on the Constructal is a new body of knowledge. Yes, okay, and it's engineering knowledge. Okay, so key thing is, you can't, science doesn't tell you how to build an airplane, doesn't tell you how to do anything really, cell phone, it doesn't do any of that stuff. So it's the art of the engineer. So in the constraint, he says, the creative constructive knowledge of the engineer is the knowledge needed to implement that art. And finally, the engineering epistemology then also has an engineering ontology, which has to do with engines and so forth. So the thing I want to say about this, I'm going to go back one step here. The thing I want to say is that engineers, so the engineer built the airplane. You can't derive the airplane from science. So the engineer understands the airplane in a way that science never will, cannot. The cell phone, the tree, anything in nature, okay? Science cannot understand these things by their very nature, okay? But engineering can. The engineer can look around the world, can understand the world in a way that science can't. This is, I think, one of Bejan's, this should be like one of his main gigs. So now my action agenda is, I want to tell Bejan, I want to get him the Nobel Prize. He's very for all this stuff, he's underappreciated, underrealized. So, and in order to do that, he has to stop saying that the Constructal law is physics, which he doesn't want to do. It's engineering. It's engineering. It isn't physics. He knows it's not physics in the old sense. He knows that when he talks about predictions, it's not prediction in the old sense. It's something else. Okay, so that's what I want to do. And I just say I did a talk on something like this a bit ago. I'm just going to run through these slides real quick. So this buddy of mine, George Bolliarello, he says system engineers should be taught that engineering is a natural extension of biological evolution. Well, okay, we're natural extension of biological evolution. But what that means is that the whole of evolution is an engineering enterprise. Okay, it's not. You can't derive it from science. Now this goes back to Plato's Timaeus and the Demiurge and so forth. The master craftsman, which is an engineer. I'm going to say one thing about the Timaeus. There's a couple of deep dives I wanted to do, but Timaeus, they ask him, how did the world come to be as it is? He said, well, I can only give you a probable answer in terms of specifics, okay, individual things. But he says, one thing's for certain, and I love this. He says, one thing's for certain, it always moves to the good. Now, the only other person that I've seen that gets this is Adrian Bejan, and that's that the design improves by its very nature, okay? Always improving by its very nature. This is, they say, that it always moves to the good. I was asking Adrian if he was actually Pythagoras. He'd been reborn as Pythagoras. Almost no one else has ever seen it. I mean, this is the first time this came up. There's an expression by Kenneth Arrow about coming up with new ideas and stuff. And Kenneth Arrow, the economist, he talks about an underground river of ideas. And he says, underground river comes up every once in a while. It came up in that period and around, from 1650 to 1850. Then it got smushed by Lagrange and, the completed calculus guys. And that's been dominating for a long time. It's come back up. It's come back up in quantum theory, but it's come back up with Bejan. And all of a sudden, this is that whole thing that was developing during that period. And I think Whitehead says the whole of the period of 20th century, 21st century thinking is based on what these people did in that period from 1650 to 1850. Okay, well, anyway, you can look at my thing, but I argue that the reality is composed of, I'm talking about structure and function, embodied intelligence. Bejan doesn't talk a lot about intelligence. He should, because the engineer's choices are intelligent choices, and they're for reasons. So that's what the world's made of. Okay, did I go over too much? Thank you for tolerating my excess. Any questions? No. Kind of over time. You have a question? Yes, go ahead.
Yeah, so I guess it's sort of a terminology question, because I think that many people have been taught that engineering is the application of science to solve problems. And you define clearly that that's not what engineering is.
Correct. Big point.
However, science is not produced in a vacuum, and there's obviously an enormous body of observationally derived science. And so maybe if you could draw a clear distinction of what is an engineer.
Well, first I'd say that observationally derived science, the people that, scaling and elementary power laws, all that sort of stuff, how do they come up with that stuff? They just observe. I mean, it's what Bejan calls this method but it's the analytics. Okay, and they don't understand it. Okay, and you can say that's science, but I think the other thing to realize is that there are no scientists in the scientific worldview, right? So they have no way of accounting for that. How do they come up with that? I mean, this is one of the philosophy of science things. The reason I got out of philosophy of science, went to philosophy of engineering, because all the accounts of how science works were all rubbish. None of them worked. Everybody knew they didn't work. Okay, so what are we doing? What is learning? How are we coming up with this knowledge? Well, there was no, one of my mentors, Paul Feyerabend, because I wrote this thing called Against Method. He said, you method of science, show it to me. Where is it? Love to have it. Doesn't exist. There is no such thing. So you want to understand discovery and invention and all that sort of stuff. It's all engineering. And you have to get into the engineering context. And Charles Sanders Peirce said all meaningful questions are in the practical context. They're engineering questions. And all knowledge is engineering knowledge. So there is no scientific knowledge.
Yeah, and I think there may be a longer conversation about the philosophy of science of what is understanding and what is knowledge, because to my view,
well, it's a key issue.
The observation of a physical principle via your senses and the creation of a mathematical model which describes it well is a mode of understanding, in my view. And so how an engineer may create a plane that flies is sort of a deeper, more meaningful level of understanding than an analytic description is something that I think is something I'd like to talk to you about.
Yeah, good. I would look forward to it.
Just really quickly, you made reference to Karl Popper.
Yes.
And so he self-categorizes himself as a philosopher of science, and he describes the scientific method using
I knew him well.
falsifiability. I'm just wondering, I guess you would account him as an engineer?
Well, Popper's the whole history of Popper is very interesting. Early Popper was sort of nuts, and he was in that same nonsense of trying to come up with a method and, one piece of evidence against a theory, knock it out and all that. Everybody realized after a while that was not the way things work. Look at Popper's last stuff. He says, all the world is problem solving. Okay? And that's engineering problem. Scientists don't solve problems. One of Petrosky's things. You want to change the world? So don't ask an engineer, or don't ask a scientist, ask an engineer. So Popper, I think, essentially morphed over his period from the philosophy of science and gross inadequacies of our representation of what is a scientific world we're on, what is a scientific method. And he goes on, he starts to go to this problem where it's STEM, like ST, the E, big E, and STEM.
I'll talk to you at the coffee break.
Okay. Love it.
Thank you for your beautiful presentation. I enjoyed it a lot.
Okay, good.
Just a comment. I believe that you are right, because science, analytical science, normally deals with a particle, a system as a particle. No structure, and if they find any structure, they go finding the ultimate particle. This is analytic. On the other side, we have engineering, where we have assemblies of particles, and we are using analytical science of the particle that can be divided just the infinite insertion of the ultimate particle. This is the science of the particle. In constructing assemblies, which is the mission of the engineer, and we are using an idea which is an asymptotic representation of the world in the real world, which is finite. And I agree with you. This is not, we cannot make an opposition between the two things. They are complementary. But we must set the limits of each representation. And I believe that you did it very, very well.
Well, the thing that I've struggled with a lot, and that's why I say to Adrian, I feel your pain because I felt the pain, and that is really trying to understand the relationship between science and engineering. And I'm getting pretty good at it, I think, now, but it's difficult, and there's a tendency to want to say that the scientific, differential equations or something like that are derivatives. That's a very tempting idea. Like there's this, because the engineering has these two aspects. So I would take the derivative one way, take the derivative another way, but that's not a function up here. Okay, this isn't a function. The constructal is not a function. It has these two things. You cannot derive particle physics and electromagnetism from quantum theory. Quantum theory is, and quantum, I wrote this paper that you want to understand quantum theory, the only way you can understand quantum theory, first of all, it's a thermodynamic theory. And it's certainly not a mechanical theory, so it's not the mechanical version of thermodynamics. What do you got? You got engineering thermodynamics. So the only way you can understand that is in terms of engineering thermodynamics. And this is the superseding thing. You need to grasp is that, for instance, in quantum theory, what you mean by position and momentum and velocity, these are different concepts. Okay, these are different concepts. They don't translate from the old concepts of position and momentum and sort of thing. They're more sophisticated concepts. That's what I say. But you also see it, of course, that freedom. There's free in quantum theory properly represented. There's freedom. It's cumulative. All those things. So, and I think that the problems that we encountered with quantum theory and the problems encountered with relativity are actually the same problems. So this whole thing, we can't get them together. Well, they actually come together with the constructal approach. I gave a paper on this in Holland a few months ago. I didn't like it exactly, but I think Christian Huygens, who was a Dutch physicist, it was crucial. He turned on Leibniz, Maupertuis, Carnot, all this sort of stuff. So I think Huygens and maybe D'Alembert were the first guys in that period to really get hold of this transition to look up something called the path of swiftest descent. I love it. Look at the path of swiftest descent. It always has two aspects. Okay, I have another question now. I'm eating into somebody's time here. just get a coffee right there.
Just really quick, you were suggesting how to secure Nobel Prize for Adrian Bejan.
Yes.
Additional suggestions on that topic.
It's not what?
Additional suggestions how to do that next to.
How to do that? Well, you understand the Nobel Prize, although it's given to scientists a lot, if you read Nobel's will, it's supposed to be given to engineers, essentially, practical people. And I think that's, would be, we could pick out any one of the things that he's figured out on that. So he should definitely have he should have 3 or 4 Nobel Prizes, depending on which one of the, Nobel, he's, medicine, physics, whatever. I mean, he's got all of them. So is there one you missed? I don't know. Peace Prize? No. Okay, so thank you, and sorry for taking so long.